Hello! Completing the square is a method of solving quadratic equations. But first, what is a square? A square, or sometimes perfect square, is any number or expression that is squared, or raised to the second power. For example, 4 is a square because it is equal to 2 squared, or 2 times 2. We say 2 raised to the second power, or 2 squared. 121 is a square because it's 11 squared, or 11 raised to the second power. X squared is squared because it's x squared, or x to the second power. The quantity x minus 5 squared is a square because it's the quantity x minus 5 raised to the second power. If you're wondering why we use the word squared for raising to the second power, it does indeed have to do with squares in the geometric sense. A square is a rectangle whose sides are all the same length. So, if we have a square whose side length is 2, then we have a square with area 2 times 2, or 2 squared. So, the area of a square with side length 2 is 4, therefore 4 is a perfect square. Let's look at this last example of a perfect square a little more closely. We can expand this expression because x minus 5 quantity squared means x minus 5 times x minus 5. If we multiply this out, it goes like this. X times x, x times negative 5. Negative 5 times x, negative 5 times negative 5. Notice the pattern. The middle term occurs twice, and it's made up of the 2 terms in our binomial. Therefore, the coefficient of the linear term here is twice the number that was in our original binomial. Also, the constant term here is the square of the number that was in our binomial. Remember this pattern. So when squaring x minus 5, we get this trinomial, which is equivalent to x minus 5 squared. They are both perfect squares because they are both just representations of the same thing. In this format, we can see what's being squared. In this format, we can't see it, but we still call it a perfect square. In this format, we often call this a perfect square trinomial. Perfect square because it can be written as something squared, and a trinomial because it has 3 terms. 1, 2, 3. So, the expression x squared minus 10x plus 25 is called a perfect square trinomial because in factored form it is a perfect square. Note one more time the pattern. The 5 in the square, the double of that here in the trinomial, and the square of that there in the trinomial. For contrast, let's look at the expression x squared minus 8x minus 20 and notice that it is not a perfect square because in factored form it is not a square at all. And notice the pattern that we just talked about does not hold. 20 is not the square of anything here, and this number is not double anything here. That pattern is not here. So completing the square is when you take an expression that is not a square, like x squared minus 8x, and give it what it needs to be a square. What number would have to go here in order for this then trinomial to be a perfect square? We have already noticed the pattern in the numbers when the trinomial is a perfect square. We know that it would have to be the square of whatever number you had to double to get this number. Well, if 8 is the double of a number, then half of 8 is the thing you double. Half of 8 is 4, and 4 squared is 16. So if we add 16, we should then have an expression that is a perfect square. Let's double check and see if this is right. It is a perfect square. It is x minus 4 squared. So that relationship, if a trinomial is a perfect square, then the constant term will be the square of half of the coefficient of the linear term. So we use this idea to solve quadratic equations. Notice this trinomial here is not a square. We know this because if it were, this number here would be the square of half of this number here. And that's not the case. So we move that number to the other side of the equation. We do that by subtracting 63 from both sides. If you want to write it down, you can. 0 on the left-hand side, negative 63 on the right. We leave a small gap here to remind us that we're going to be adding something to complete the square on the left-hand side. We know that the number we add has to be the square of half of 16. If we want to write it down, we take half of 16 and we square it. Notice I'm ignoring the sign of the 16. Technically it's negative 16. I'm ignoring it because I know that when I square, it will be positive anyway. Half of 16 is 8, and 8 squared is 64. So the left-hand side needs a 64 in order to be a perfect square. But if I add 64 to the left-hand side, I have to add 64 to the right-hand side. And now the left-hand side is a perfect square, so can be written as x minus 8 squared. on the right-hand side can be simplified to 1. Now we are in the position to use the square root property. I put a line there to give myself a boundary between the work I just did and the work I'm about to do. So if x minus 8 squared equals 1, then x minus 8 must be plus or minus the square root of 1. And since the square root of 1 is 1, and adding 8 to both sides to isolate the x, we get x is equal to 8 plus or minus 1, which gives us two numbers. X equals 8 plus 1, which is 9, and x equals 8 minus 1, which is 7. Therefore, the solutions to the original equation are 7 and 9. I like to write them in order. If we were to check these by plugging 7 or 9 back into the original equation, we would get a true statement. When x is 7, the left-hand side will equal 0, and that matches the right-hand side. When x is 9, the left-hand side will be 0, and so will the right-hand side. Let's do one more. I didn't mention this before, but it's important to understand that completing the square cannot be done if the leading coefficient, or the coefficient of the squared term, is not 1. In other words, that coefficient must be 1 in order to use the method of completing the square. But that's not a problem, because we can always factor out something to make it a 1. In this case, since it's a 4, we factor out 4. I like to double check my work sometimes. 4 times x squared is 4x squared, 4 times 2x is 8x, and 4 times 5 is 20. Now we can divide both sides by 4 to get rid of that 4. 4 divided by 4 is 1, and 0 divided by 4 is 0. If you have nothing and you divide it into 4 parts, each part is still nothing. Now we've got a trinomial whose leading coefficient is 1. We also notice that it is not a perfect square because the pattern for a perfect square does not hold. This number is not the square of half of this number. So we rearrange the equation and add to both sides the number that is the proper one to make the left-hand side a perfect square. Half of 2 squared is the number we need. Half of this number squared is what we add to both sides of the equation. Half of 2 is 1, and 1 squared is 1. So we are going to add 1 to both sides of the equation. Now the right-hand side is a perfect square that factors into x plus 1 squared. And the left-hand side simplifies to -4. Now we have a number represented by x plus 1 that is squared that equals -4. It's okay that it's negative, as we know that complex numbers have negative squares. Now we are in a position to use the square root property, since we have something squared equals a number. So if x plus 1 squared equals -4, then x plus 1, the thing being squared on the left-hand side, has to be plus or minus the square root of negative 4. Let's simplify the right-hand side. The square root of a negative number always introduces an I, as we know. And then the square root of 4 is just 2. So you could write I2, but we would not write that. We would write plus or minus 2i. And now we isolate the x by adding the opposite of 1 to both sides, or that's equivalent to subtracting 1 from both sides. If you wanted to write it down, you could do it like this. Just know that even if you write it down like that, these things cannot be combined for a number of reasons. One reason is that this is not a single number. It's actually two numbers. And so we don't know, we have two different numbers to combine with a negative 1. Also, these two numbers are not like terms. One has an I and one does not, so they won't be combined together anyway. On this side, the ones cancel out. We get x equals negative 1 plus or minus 2i. We like to put the plus or minus in the middle. So that is actually two numbers, negative 1 plus 2i and negative 1 minus 2i. And these are the two solutions to our quadratic equation.